Welcome to this lesson on AP Statistics. Today, we are diving into Topic 3.3, Constructing a Confidence Interval for a Population Proportion. By the end of this video, you will be able to identify the correct procedure for estimating a population proportion, verify if the data meets the requirements for this procedure, and perform the actual calculations to create an interval. We will also look at how to determine how large a sample needs to be to reach a specific level of precision. Let's start with the big idea. In statistics, we often want to know a parameter, a true value about an entire population, like the proportion of all teenagers who own a smartphone. Since we can't ask every single teenager, we use a sample proportion, p hat, to estimate it. A confidence interval gives us a range of plausible values for that unknown population proportion. The specific procedure we use for this is called a one-sample z-interval for a population proportion. Before we can start crunching numbers, we must ensure that our statistical foundation is solid. We do this by checking three specific conditions. If these aren't met, our interval might be misleading. The first is the randomization condition. The data should be collected using a random sample. This helps ensure that our sample is representative of the population and minimizes bias. The second is the 10% condition. When we are sampling without replacement, which is almost always the case in the real world, the population size, capital N, must be at least 10 times larger than the sample size, little n. This allows us to treat the individual observations as independent. Finally, we have the normality condition, often called the large counts condition. We need to see at least 10 successes and at least 10 failures in our sample. If we have both, the sampling distribution of p hat will be approximately normal, which justifies our use of the z-score later on. Now that we have checked our conditions, let's talk about what the interval actually looks like. Every confidence interval follows a basic structure. It is a point estimate plus or minus a margin of error. For a population proportion, our point estimate is p hat, the proportion we found in our sample. The margin of error is made of two parts, a critical value and the standard error. The critical value, written as z star, depends on how confident we want to be. Usually 90, 95, or 99%. It represents how many standard deviations away from the mean we need to go to capture that middle percentage of the normal distribution. The standard error, or SE, of p hat is our estimate of the standard deviation of the sampling distribution. Since we don't know the true population proportion p hat, to calculate it, putting it all together, the full formula for a one-sample z-interval is p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. This formula gives us the range of values that we are C% confident contains the true population proportion. Let's put this into practice with a concrete example. Suppose we want to estimate the proportion of students at a very large university who drink coffee every morning. Our sample size is 200 students, with 120 identified as coffee drinkers, and we want a 95% confidence level. First, we define our parameter p. It is the true proportion of all students at this university who drink coffee every morning. Next, we calculate our point estimate, p hat. This is 120 divided by 200, which equals 0.60. 60% of our sample drinks coffee. Now, let's verify the conditions. First, randomization. We assume we took a simple random sample. Second, the 10% condition. 200 is definitely less than 10% of all students at a very large university. Third, normality, or the large counts condition. Successes equal 120, and failures equal 200 minus 120, which is 80. Both are at least 10. The conditions are met. For a 95% confidence level, the standard critical value z-star is 1.96. This is the z-score that cuts off the middle 95% of a normal curve. Now we calculate the standard error. It is the square root of p hat times 1 minus p hat, all over n. This simplifies to the square root of 0.24 over 200, which is approximately 0.0346. Finally, the margin of error is z star times the standard error. 1.96 times 0.0346 is approximately 0.0678. Our interval is our point estimate, 0.60 plus or minus 0.0678. This gives us an interval from 0.5322 to 0.6678. We are 95% confident that the true proportion of students who drink coffee is between 53.22% and 66.78%. Sometimes, researchers have a specific goal in mind for their precision. They might say, I want to estimate a proportion, but I want my margin of error to be no more than 3%. To achieve this, we need to determine the minimum sample size, little n, before we even start collecting data. To solve for the sample size n, let's look at our formula. Recall that our margin of error, which we will call MOE, is equal to the critical value z star times the standard error. To find n, we can rearrange this formula using algebra. Now, here is a common hurdle. If we haven't done the study yet, we don't know what p hat is. In these cases, we use a conservative estimate of p hat equals 0.5. Why 0.5? Let's look at the graph of the numerator. Mathematically, the product of p hat and 1 minus p hat is largest when p hat is 0.5. By using this value, we are planning for the worst-case scenario regarding variability. This ensures that our sample size will be large enough to meet our margin of error goal, regardless of what the actual sample proportion turns out to be. If we use any other value for p hat, the required sample size would be smaller. Using 0.5 gives us a safe upper bound for the sample size. One final crucial rule for sample size. Because you can't survey a fraction of a person, you must always round your final answer up to the nearest whole number, even if the decimal is very small. If you round down, your margin of error will be slightly larger than your target. Let's work through a sample size problem. Suppose a company wants to estimate the proportion of customers satisfied with a new product. They want to be 99% confident that their estimate is within 4 percentage points of the true population proportion. How many customers must they survey? First, we identify our critical value z star for a 99% confidence level. Using a standard normal table or calculator, we find that z star is approximately 2.576. Since we don't have a preliminary estimate for the proportion of satisfied customers, we will use the most conservative estimate to ensure our sample is large enough. Now, let's plug these values into our rearranged formula for n. Substituting our values, we get n equals 2.576 divided by 0.04 squared times 0.5 times 0.5. Let's calculate the fraction inside the parentheses first. 2.576 divided by 0.04 equals 64.4. Squaring 64.4 gives us 4,147.36. Multiplying that by 0.25 gives us 1,036.84. Remember our rule. Always round up to the next whole number to guarantee the margin of error is not exceeded. The company needs to survey at least 1,037 customers to be 99% confident that their sample proportion is within 4% of the true population proportion. If they surveyed only 1,036, their margin of error would technically be slightly larger than 0.04. It is also important to understand the difference between the standard deviation of a statistic and its standard error. While they look similar, they are used in different contexts. The standard deviation of the sample proportion, p hat, describes how much the sample proportion varies from sample to sample across all possible samples of size n. To calculate this, we use the true population proportion, p. However, in the real world, we almost never know the true value of p. That is exactly why we are building a confidence interval in the first place. This leads us to the standard error. The standard error is our best estimate of that standard deviation, using the data we actually have on hand. The standard error quantifies the typical amount that our sample proportion, p hat, will vary from the true population parameter p. If we have a large standard error, our estimate is less precise. If we have a small standard error, our estimate is more precise. Looking at the formula, you can see that the sample size, n, is in the denominator. This means that as the sample size increases, the standard error decreases. This makes intuitive sense. A larger sample gives us more information and a more consistent estimate of the truth. To wrap up, let's review the core concepts we've covered today for topic 3.3. You are now equipped to handle confidence intervals for proportions from start to finish. We have covered the one sample z interval procedure, the 3 essential conditions, the interval calculation, and how to plan for sample size. We started by identifying the one sample z interval as the appropriate procedure for estimating a population proportion. We learned that before performing any calculations, we must verify the randomization condition, the 10% condition for independence, and the normality condition, which requires at least 10 successes and 10 failures. We saw how the standard error estimates the typical distance between our sample proportion and the true population proportion, and how the margin of error uses a critical value, z star, to create our range of plausible values. Finally, we looked at how to plan a study by solving for the minimum sample size n. remembering to use 0.5 as a conservative estimate for p-hat and to always round up to the nearest whole person or object. Confidence intervals are a powerful tool because they allow us to admit that we don't know the exact truth, while still providing a mathematically sound range where that truth is likely to hide. Thank you for watching. Practice these calculations and condition checks, and you will be well on your way to mastering AP statistics. Great job today!